New reinforcement learning algorithm DCPO fixes two major issues with DeepSeek's GRPO to make it train a lot faster. First of all, in other reinforcement learning algorithms like GRPO by DeepSeek, the way it works is you have a prompt, a question, and model generates 16 answers, and you see which ones are correct, which ones are wrong. So, and then you see what's the average. If like half are correct, half are wrong, the average is half a point. And so if only one is correct and all are wrong, then that one will get very high reward because the advantage, so it will have high advantage because it's the only one correct while all others are wrong. So you want to reward that one correct reasoning path, those tokens. You want to make those tokens that lead to that reasoning path a lot higher probability. So the reward, the probability increase or decrease for each of the answers tokens depends on first the average. If it's a difficult question, then most of them got wrong, then the correct one or two will get huge rewards, so their tokens will get a lot more probability, a lot likelier next time. Or if it's an easy question, but there is just a few that got wrong and most got correct, then you want to punish those wrong ones harder and make their token chain less likely to happen next time. Now, this is the problem in GRPO. If all of them are wrong, then any one of them is not better or worse than the average, because average is 0 and everyone is 0. So there is GRPO doesn't learn anything from there. Or if all of them are correct, GRPO doesn't learn everything from there. So different methods find different ways of dealing with this. One common method is just to ignore or delete those examples where all of the answers are wrong or all of the answers are correct. But this leads to wasted time because model is generating those answers and it's wasting time because those answers are going to get deleted. The way DCPO solves this problem is it doesn't just look at the current 16, for example, answers, if they're all wrong. It also looks at how in the past model performed on this question. Maybe in the past it actually got some correct and now all are wrong. So now model is performing worse. Or maybe now all are correct, but in the past some were wrong. So now model is performing better. So the reward will be calculated based on the past examples as well. So it's measuring against all of the answers in entire history of this prompt, of this task. And it's keeping mean and standard deviation of all of the answers and if it's correct or not. So of the reward, it keeps the mean and STD of the reward. The second problem DCPO solves is that update clipping. So check this out. When we are rewarding the model, what that means is we are changing probabilities of the tokens so that correct tokens have higher probability of appearing next time, the answers that were correct. But we don't want to change these probabilities a lot. What can happen is that some random lucky, maybe like lucky response or response that had some even incorrect tokens that led to correct answer, or for example, some case where it's too difficult, but some lucky response that's not even like intelligent or smart, it just got lucky. So what can happen there is that this single lucky response can get huge reward, and then it can modify a lot the probabilities to increase those tokens, but it's not a good thing because this was just lucky, it's not intelligent. So usually they clip how much each token's probability can change. For example, if it can only go up and down by 20%. So if it wants to if model wants to make it 5 times more probable, it's not gonna happen. It's gonna get clipped to 20%. And same goes for less probable. The problem here is that smart answers, creative answers can come from some random unexpected tokens that actually had low probability. They are not expected, they have low probability. But model finds these tokens and then starts increasing their probabilities because their probability should be a lot higher. They're not expected, they should be expected. but then this clipping will interfere with that. So now they have dynamic, not static fixed clipping threshold. They have a dynamic based on original tokens probability. So for very low probability tokens, unexpected tokens, they're gonna let them change their probability a lot more, because they could be the secret to the answer, the unexpected, what LLM needs to learn. But for tokens that are already common, that already have high probability, we wanna clip those a lot more, because those random fluctuations, lucky answers can change those probabilities a lot up and down. But we don't want like that to happen. So for common tokens that are already good, already common and expected, we want to just clip their change. We want to stabilize them. And we want to allow rare tokens to change probabilities a lot more. To summarize this token clipping, we want to mitigate the effect of lucky guesses. And we're going to do that by applying a strict clipping on probability change of the common tokens. But we don't want this to prevent rare tokens that are actually good and useful becoming more common and making LLM smarter. So we're gonna make the clipping of rare token probability updates a lot wider. So we're gonna allow rare tokens to jump up in probability a lot more.